Günaydın. Today, I'll start discussing motion. We have now already gone through all the tools. We have discussed the philosophical foundations of science. We have talked about how to write numbers, how to calculate units, dimensions, errors, etc. And we have learned about vectors. Okay, so we have now got everything to start. Then, how do we describe motion? We have a coordinate for a point, x, y, z. If this point describes the position of an object in space, as the object moves, the next moment in time, it will be at a different position, and the position x, y, z, or the position vector from the origin, will change as time goes on because the object is moving. Okay? So, the description of motion will involve a path or trajectory of the motion as the coordinate of my object, or the object itself, moves through space. Its position changes as a function of time, and it describes some kind of curve, line. That's just the path, the route that the object follows. Okay? Now, you may ask, well, how come I describe the motion of an object with just one point? Because most objects are not points, they are big. Okay? This is just the beginning, an approximation. If the object is a rigid object, a solid object that does not change its shape, then there is one point in it, we will learn later, which is called the center of mass. And the general motion of this object is how the center of mass, how its center moves. So that's a point. It's a mathematical point. Okay? In addition, the object, while its center of mass moves, the object may turn around, rotate. That's all a solid object can do. Okay, it can change its orientation. It can rotate around its center of mass. So we are justified in just considering the center of mass. If my object is a big object that's also fluid, like a liquid or a gas, for example, a cloud, then again you can describe this motion with the center of mass. But with respect to the center of mass, the motion of the object, the motion of its different parts with respect to each other, is more complicated than for a solid body because it can rotate, but if it's fluid, it can also change its shape. You watch a cloud, what happens? The cloud moves, and at the same time, the shape of the cloud changes because the little particles making up the water molecules making up the cloud, okay, are moving around. Okay? So coming back to my question, of course most objects are big, but there's always one point in the object which is important to describe the overall motion of the whole object. So we can concentrate on that object, on that point. So either we are assuming the object is very, very small compared to the dimensions of our measuring apparatus, or the object may be big and we are concentrating on the motion of a representative point, the center of mass in the object. Okay. So mathematically we have just x, y, z, and these are changing as time goes on. X, y, and z, the coordinates, are all functions of time. And as time goes on, the point moves along, and we call this the trajectory. Of course, knowing the trajectory is not enough to describe the motion. Along the same path, the particle may move with different speeds, different velocities. So to really describe the motion as time goes on, one must also know not just where the particle is, but one must also know how fast it's moving from one position to the other. Okay? This is what we'll learn today. Now, to simplify things, I will concentrate on one-dimensional motion. This means the object is moving along a straight line. Okay, so it's moving along some kind of speed to here, and then maybe it's moving slower, faster. Maybe it comes back and then moves forward again. But it's always moving along a straight line. It's enough to learn how to handle this one-dimensional motion, because if you know how to handle one dimension, x of t, then the same applies to what happens for the y and z components of the motion. And the general motion is just a combination of x motion and y motion and z motion makes this. Okay? So it's not necessary to consider right from the beginning the whole vector x, y, z of t. We'll just do x of t, and that will be enough to learn how to calculate velocities, how to handle, how to follow motion. All right? Now, in one dimension, okay, we have x, that's our interesting variable. We are watching where the particle is. And that depends on time. So x is a function of time. So we can graph it. What does that mean? We want to understand how x varies with time. So we put time on one axis, and x is a function of time on the other axis. And we keep making our measurements. At t equals 0, let's say, our particle is here. At t equals 1, the particle is here. What does here mean? For example, at t equals 0, the particle, let's say, was here, 0. And at t equals 1, it's here. At t equals 2, it's come back over here, let's say. See? And then you just note these positions. At t equals 0, the position was 2 meters from my origin. At t equals 1, it went back to 1.5 meters. At t equals 2, it was at 3 meters, etc. So I note against each time, so many seconds, the position, so many meters, plus or minus, with respect to some reference point, some origin. Okay? Then I can plot this. I can graph it. I just note all my measurements and then join them up. Okay? And that is the trajectory. That is the trajectory graphed as a function of time. The actual trajectory in one dimension is this. This is what the particle is actually doing. For example, it can be a little bead, boncuk, on a straight wire. It's moving back and forth because some force is acting on it. Okay? And then you plot it. The plot is this. All right? Any questions?